Today, we're going to learn the alternating series test, and this is going to allow us to deal with series that involve both positive and negative terms. So if you think about all the other tests that we've learned so far, one of the conditions that we had to start out with is assuming that we had all positive terms, like the integral test, the direct comparison test, the limit comparison test. So if we had negative terms in there, especially like alternating between positive and negative things, those tests don't work. So that's where the alternating series test is going to come into play. And so an alternating series is just a series whose terms alternate between positive and negative terms. So we could start with positive and then go negative, positive, negative, positive, negative, or we could go negative, positive, negative, positive. Doesn't really matter. Let's just get some practice writing the summation notation for both of these before we decide whether these converge or diverge. So I like to forget about the negative signs when I write the sum and then come back and think about the negatives. So if I just had 1/2, 1/3, 1/4, that looks like the harmonic series. So this would be 1 over n from 1 to infinity. But then we have those negative signs. And so the way to account for a negative sign is to put a -1 to the n in here somewhere. And we're either going to do, we can either use -1 to the n or -1 to the n plus 1, which is equivalent to -1 to the n minus 1. And we just have to figure out which of these we have to use to get the negatives in the right spot. So in this case, I see if I plug 1 in, -1 to the n will be negative, but my first term is supposed to be positive. So let's make this n plus 1. Alternatively, you could make that n minus 1 and that would work. So now if I plug n equals 1 in, I get 2 in the exponent. So I get -1 squared, which is positive. So it looks like this will work. You could check a few other terms just to make sure that this actually works. Okay, this is called the alternating harmonic series because notice it started out as the harmonic series, but then the signs alternate. So this is the alternating harmonic. We know that the harmonic series diverges. If I add up all those terms, they do not approach a particular number. Now we wonder whether the alternating harmonic series converges or diverges. We notice since we're subtracting some terms, it's possible that this sum gets closer to a particular number. So the alternating harmonic might converge. We'll figure that out in a minute. Let's look at this other sum. So again, if I forget about the negative signs, I have 1/2, 2/3, 3/4, 4/5. So it looks like the numerator is n and the denominator is n plus 1, where we start from 1 to infinity. Again, we need a -1 in here. It looks like -1 to the n will give us the negatives in the correct spots. Okay, so let's determine whether these series converge or diverge and how we figure that out. So that is the alternating series test. So the alternating series test has 3 conditions that we have to check. So the first condition is that we have to be working with an alternating series. Alternating series test does not work if our series is not alternating. Imagine that. So check to make sure your series is alternating. And then we look at the absolute value. We forget about the negatives and we check 2 conditions about that. So we want that sequence of terms to be decreasing, or at least eventually decreasing. If the first couple terms are increasing, but then it starts decreasing forever, that's okay. And then we also want the limit of the positive pieces to be equal to 0. If all 3 of these conditions hold, then the alternating series test tells us that that alternating series is convergent. Okay, notice the alternating series test tells us nothing about divergence. If one of these conditions is not satisfied, we don't know anything. Okay, be careful. Alternating series test, never going to tell you that a series diverges. Okay, so let's go and try and apply alternating series test to these 2 cases up here. So if I look at that alternating harmonic, I'm going to go ahead and write down my conditions. So it is indeed alternating. Cool. Okay, so now I need to look at the positive pieces. So if I look at the absolute value here, the positive pieces are just 1 over n. So this is the sequence that we're calling b sub n in that definition. So I need to look at the limit of those positive pieces. Okay, that limit is definitely 0. That's good. That's what we wanted. And if I look at 1 over n as a sequence, that is definitely decreasing. Each term is getting smaller. Okay, Okay, so all three conditions of the alternating series test are met. So that means that our series is convergent. So the alternating harmonic series converges, which is kind of interesting. Convergent by the alternating series test, which I'll abbreviate AST. Okay. Next class, we're going to learn what happens. This one's kind of interesting because the alternating series converges, but if I looked at the absolute value, that would be the harmonic series that diverges. So this is going to be something we'll talk about, conditional versus absolute convergence. And that's going to be like, well, does the absolute value can diverge, but the original series not? So that's something we'll talk about eventually. Okay, so let's look at this next one. So again, this is alternating. Okay, if I look at the absolute values here, the series we get, or the sequence we get, is n over n plus 1. Okay, so I can look at that limit as n approaches infinity of n over n plus 1. And uh-oh, we've got a problem. That limit is equal to 1. You could use L'Hopital's rule there, or you could look at the highest powers. That's not 0. Oh, that's sad. That means the alternating series test tells us nothing. Okay, but we still have an alternating series. So what do we do when the alternating series test doesn't work? Usually we try a test for divergence because we see that this limit here gave us 1 out. Which is not 0, so the test for divergence might work, but we have to apply the test for divergence back to the original thing, to the alternating piece. So let's try a test for divergence here. So if we look at a limit as n approaches infinity, it's a sad looking infinity, of -1 to the n times n over n plus 1. Let's think about what this does. So we know that the n over n plus 1 approaches 1. And what that -1 to the n does is that tells us that some of these terms are going to approach +1 and some of the terms are going to approach -1. So what's going to happen towards infinity is we're going to have part of our series going towards 1, part of it going towards -1, which is going to tell us that this limit does not exist. Because if we have values going toward 2 different places, our limit does not exist. Okay, does not exist is not equal to 0. So that means that the test for divergence, so by the test for divergence, our series, our alternating series, diverges. Okay, and oftentimes this is going to be what you do. If the alternating series test does not work, it's usually not going to work because that limit condition is not met. And if that limit condition is not met, a very similar argument to what I just did usually works to show that that limit of the alternating pieces does not exist. And so the test for divergence can kick in. Okay, so this is the alternating series test.